Preparing for a software engineering at LTTS interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you explain the software development lifecycle, and how do you contribute at each stage? The software development lifecycle provides a controlled path from requirements to maintenance. I clarify requirements, identify risks, and help define a practical design before coding. During implementation, I follow coding standards, use version control, and request reviews. I create unit and integration tests, support system testing, and document behavior. After release, I monitor defects and performance, then feed lessons into the next iteration. For client projects, traceability and regular communication are especially important. While answering, cover requirements analysis, architecture, implementation, code review, testing, deployment, maintenance, documentation, traceability, and how you communicate risks across distributed client and engineering teams. Question 2. Describe your approach to gathering and clarifying requirements from a client or product owner. Ambiguous requirements create expensive rework, so I make them testable early. I ask targeted questions about users, inputs, outputs, constraints, failure behavior, security, and performance. I convert answers into user stories or specifications with acceptance criteria and examples. Then I review the document with stakeholders and record assumptions and open decisions. If priorities change, I assess impact on scope, schedule, and quality before agreeing to an updated baseline. Make sure to cover active listening, functional and non-functional requirements, assumptions, edge cases, acceptance criteria, prioritization, written confirmation, stakeholder alignment, and handling ambiguous or changing requirements. Question 3. Which object-oriented design principles do you apply in production software? I use object-oriented design to keep responsibilities clear and changes localized. Encapsulation protects invariants, while abstraction exposes only useful behavior. I generally prefer composition over inheritance because composed components are easier to replace and test. Solid principles guide decisions, but I avoid applying patterns mechanically. For example, dependency injection lets a service use a mock repository during unit testing. The goal is high cohesion, low coupling, and understandable code rather than elaborate class hierarchies. In your answer, discuss encapsulation, abstraction, inheritance versus composition, polymorphism, solid principles, cohesion, coupling, testability, and examples showing when a design choice improves maintainability. Question 4. How do you choose between C++, Java, Python, and JavaScript for a project? I choose a language based on constraints rather than preference. For embedded or real-time components, C or C++ may provide deterministic performance and hardware access. Java suits portable enterprise services with strong libraries and managed memory. Python accelerates automation, testing, and data workflows, while JavaScript fits browser and Node.js applications. I also consider team capability, security, tooling, deployment, and long-term maintenance. A small benchmark or prototype can validate assumptions before commitment. Be sure to mention performance, memory control, ecosystem, portability, team expertise, safety, deployment environment, maintainability, tooling, real-time constraints, and matching language choice to project risks. Question 5. What is the difference between a process and a thread, and when would you use each? A process has its own address space and stronger isolation, while threads share memory within a process. Threads are cheaper for coordinating related work, but shared state introduces race conditions and synchronization problems. Processes provide better fault containment and security, though inter-process communication costs more. I use threads for independent tasks inside one reliable service and processes when isolation matters. In either case, I measure workload characteristics before choosing concurrency over simpler sequential execution. Focus on address space, isolation, communication, creation cost, shared memory, synchronization, failure containment, concurrency, parallelism, and examples relevant to services, testing, or embedded applications. Question 6. How would you investigate a production defect that cannot be reproduced locally? I first assess impact and stabilize the system through rollback, throttling, or a feature flag if necessary. Then I compare production and local versions, configuration, dependencies, data, timing, and hardware. I inspect structured logs, metrics, traces, and customer examples, adding safe diagnostics when evidence is insufficient. Once I isolate the cause, I reproduce it in a representative environment, implement a targeted fix, add a regression test, and document both root cause and prevention. Cover incident triage, logs, metrics, traces, environment comparison, input capture, version verification, feature flags, controlled reproduction, safe mitigation, root cause analysis, and prevention through regression tests. Question 7. What makes unit tests effective, and how are they different from integration tests? A unit test verifies one small behavior in isolation, runs quickly, and produces the same result repeatedly. I use stubs or mocks for external dependencies, then assert observable outcomes and important errors. Integration tests verify collaboration with databases, services, devices, or files, so they are slower but catch configuration and contract problems. I use both layers, prioritize business-critical paths and edge cases, and treat coverage as a signal rather than proof of correctness. Mention isolation, determinism, fast feedback, meaningful assertions, test boundaries, mocks or stubs, integration with real dependencies, coverage limitations, edge cases, and avoiding brittle implementation-based tests. Question 8. Explain the difference between black box, white box, and gray box testing. Black box testing evaluates behavior from requirements without knowing internal implementation. API and acceptance tests commonly use this approach. White box testing uses code knowledge to target branches, conditions, paths, and error handling, which is valuable for unit testing. Gray box testing combines external behavior with limited architectural knowledge, such as testing an API while understanding its database model. I use all three because requirement coverage and structural coverage reveal different classes of defects. In your answer, distinguish knowledge of implementation, test design perspective, suitable testing levels, strengths and limitations, requirements coverage, code coverage, and examples from APIs or embedded systems. Question 9. How do you use Git effectively when multiple developers and teams are working on the same codebase? I keep commits small, focused, and easy to review, with messages describing intent. I branch from an updated mainline, rebase or merge carefully, and resolve conflicts by understanding behavior rather than choosing files blindly. Pull requests include context, tests, and known limitations, while protected branches require review and automation. I tag releases and avoid committing credentials or generated artifacts. The exact branching model matters less than integration discipline and frequent synchronization. Discuss branch strategy, small commits, meaningful messages, pull requests, rebasing or merging, conflict resolution, code review, tagging, release branches, protected branches, and avoiding committed secrets. Question 10. What is continuous integration, and how would you improve a failing C pipeline? Continuous integration validates every change through repeatable automated checks. If a pipeline fails, I identify whether the cause is code, environment, dependency, infrastructure, or flakiness rather than rerunning blindly. I inspect logs, reproduce the failure locally or in a container, and fix the underlying issue. I keep fast checks early, quarantine and repair flaky tests, pin important dependencies, publish useful artifacts, and make quality gates visible without hiding legitimate failures. Be sure to cover automated builds, unit and integration tests, static analysis, artifacts, reproducibility, failure classification, flaky tests, dependency management, feedback speed, and quality gates. Question 11. How would you design a reliable REST API for an engineering application? I model the API around resources and use HTTP semantics consistently. Get reads, post creates, put replaces, and delete removes. Requests are validated at the boundary, errors use a stable structure, and mutating operations support idempotency where retries are possible. I add authentication, authorization, rate limits, pagination, correlation IDs, and metrics. Versioning and backward compatibility protect clients. I also publish an OpenAPI contract and test both success and failure scenarios. Cover resource modeling, HTTP methods and status codes, validation, idempotency, authentication, authorization, versioning, pagination, error contracts, observability, rate limiting, and backward compatibility. Question 12. What database design considerations would you evaluate for a new application? I begin with entities, relationships, access patterns, volume, growth, and consistency requirements. Relational databases suit structured data and transactional integrity. NoSQL can fit flexible schemas or high-scale access patterns. I normalize initially, then add carefully justified denormalization and indexes based on measured queries. I define constraints, migration and rollback plans, backups, retention, encryption, and access control. The right design balances correctness, operational simplicity, performance, and future change. Mention access patterns, relational versus NoSQL choices, normalization, indexing, transactions, consistency, constraints, migration strategy, backup, recovery, scalability, security, and data lifecycle. Question 13. How would you optimize a slow application without compromising correctness? I measure before changing code, using profiling, traces, query plans, and representative workloads to locate the bottleneck. I first address algorithmic issues, unnecessary I/O, inefficient queries, serialization, or excessive allocations. Caching, batching, indexing, and concurrency can help, but each introduces invalidation, memory, or consistency risks. I establish benchmarks and correctness tests, compare results under realistic load, and monitor production after release. Optimization is successful only when user-visible performance improves safely. Focus on measurement first, profiling, latency budgets, algorithmic complexity, database query plans, caching, batching, concurrency, memory, regression benchmarks, and validating improvements under realistic workloads. Question 14. Explain common race conditions and how you prevent them. A race condition occurs when results depend on unpredictable timing between concurrent operations. A check-then-act sequence can fail when another thread changes the value between those steps. I prevent races by reducing shared mutable state, using immutable data or message passing, and protecting critical sections with appropriate locks or atomic operations. I define lock ordering to reduce deadlocks and use stress tests, sanitizers, and code review to expose timing-sensitive defects. Include shared mutable state, lost updates, check-then-act errors, locks, atomic operations, immutability, message passing, lock ordering, deadlocks, thread-safe collections, and stress testing. Question 15. What is memory management, and what problems can occur in C or C++ software? Memory management controls how objects are allocated, used, and released. Common C and C++ failures include leaks, dangling pointers, double freeze, buffer overflows, and use after free bugs. I prefer RAII and smart pointers with clear ownership in modern C++, validate lengths at boundaries, and avoid raw ownership where possible. I use sanitizers, static analysis, and targeted tests to detect issues. For embedded systems, I also consider fragmentation, deterministic allocation, and limited memory budgets. Discuss stack and heap, allocation and deallocation, ownership, leaks, dangling pointers, buffer overflows, double freeze, RAII, smart pointers, bounds checking, sanitizers, and defensive interfaces. Question 16. How would you secure a service or device-facing application? I start with threat modeling to identify assets, trust boundaries, attackers, and likely abuse cases. I enforce authentication and least privilege authorization, validate inputs, use secure transport, and protect secrets through managed configuration rather than source code. Device-facing systems may also need certificate identity, replay protection, and signed updates. I keep dependencies patched, avoid sensitive logs, run static and dynamic security tests, and design monitoring for suspicious behavior in rapid response. Make sure to cover threat modeling, authentication, authorization, input validation, least privilege, secure transport, secrets management, dependency updates, logging, replay protection, and security testing. Question 17. How do you approach software development for embedded or real-time systems? Embedded and real-time software must satisfy functional behavior and timing deadlines under constrained resources. I define timing budgets, minimize unpredictable allocation, design clear interrupt and task boundaries, and protect shared data. Hardware interfaces need defensive validation and well-defined failure behavior. I test with simulation, mocks, static analysis, and hardware-in-the-loop environments, measuring latency and resource usage. Requirements traceability and deterministic recovery are essential, especially when failures affect safety or connected products. Discuss timing deadlines, determinism, resource constraints, hardware interfaces, interrupts, concurrency, memory safety, fault handling, simulation, hardware-in-the-loop testing, and traceability. Question 18. Tell me about a time you disagreed with a code review comment or technical decision. When I disagree, I first verify that I understand the reviewer's concern and connect it to requirements or operational risk. I explain my reasoning with a small example, benchmark, or test rather than personal preference. If both options remain reasonable, I discuss maintainability and team conventions, then accept the decision or suggest a focused experiment. After alignment, I implement consistently and record important trade-offs. Healthy review should improve the product, not establish ownership. In your answer, show respectful communication, evidence, maintainability, requirements, alternatives, experiments, willingness to change, decision records, and prioritizing team outcomes over personal preference. Question 19. How do you manage changing priorities across multiple client or project commitments? I make competing work visible by ranking requests against business impact, deadlines, dependencies, and risk. For a new urgent item, I estimate its effort and explain what will move, rather than silently overcommitting. I confirm priorities with the relevant lead or client, split work into milestones, and protect essential testing and review. If capacity is insufficient, I escalate early with options and trade-offs. Clear expectations are more valuable than optimistic delivery dates. Cover impact assessment, urgency versus importance, dependency mapping, transparent communication, estimation, risk escalation, negotiated scope, documentation, time boxing, and protecting quality despite schedule pressure. Question 20. Why do you want to join LTTS, and how would you add value as a software engineer? LTTS interests me because it applies engineering and digital technology to complex products across domains, including transportation, industrial, and connected systems. I would add value through disciplined development, strong testing, and clear communication with both technical and client stakeholders. I am comfortable learning unfamiliar domains, understanding requirements, and taking ownership from implementation through defect resolution. I also bring a continuous improvement mindset. Automate repetitive work, document decisions, and leave systems easier to maintain. Be sure to connect LTTS's engineering and digital solutions work with your skills, learning mindset, client collaboration, quality ownership, adaptability, domain interest, and measurable contribution to projects. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.